Hello students, good evening all. So welcome back to our next session of chapter differential equations. So far we have finished 4 sessions in this particular chapter. So this will be our last session in this chapter of differential equations. So we have almost discussed each of the topic very clearly. So we are getting into our last topic, so in which we are going to discuss in our today's session. So before getting into our today's session, I'll just give you a quick recap of what are the concepts that we have covered in our previous session, as well as what and all the topics that we are going to discuss in our today's session. So in meanwhile time, the remaining students can also join the session. So let's have a quick recap. So in our previous sessions, we have discussed homogeneous differential equation. So how to typically solve a homogeneous differential equation we have seen. And if there is an equation which is in the format of dy by dx equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2. So if there is any differential equation of this typical form, we have seen how to reduce this form of differential equation into the homogeneous form, and as usual, after reducing that into a homogeneous differential equation format, we guys are aware of doing the solving the homogeneous differential equation. So that will be the same format. So coming to our today's session, we are going to discuss our next methods of solving differential equation, which is method of solving linear differential equations. So the next method is here linear differential equation. So how method of solving linear differential equation. So first here we have to identify the standard format of a typical linear differential equation, and once we get the idea of a standard format of linear differential equation, then we'll be having our methodology, then we'll be obtaining that, and we can easily apply and simplify in order to solve the linear differential equation. Right, and the next one here is Bernoulli's equation. So for even Bernoulli's equation, we'll be having some standard format. So we can actually reduce this Bernoulli's equation into our linear differential equation format. And again, once we have reduced that into linear differential equation, so we'll be learning here how to solve a linear differential equation. So that's what we are going to apply here and simplifying it in order to get the solution of that Bernoulli's equation. And the last type of last differential equation format which we are having here is exact differential equation. So we'll be having a standard exact differential equation. So basically what are the steps involved in it? So how we actually solve that exact differential equation in order to find the solution. So that we are going to have a look here. So these are the only leftover 3 concepts in our entire chapter of differential equations. So remaining concepts, everything we have covered in our previous sessions of differential equations. So these are our 3 concepts that we are going to discuss here in our today's session, and correspondingly as usual we are going to deal questions. So we are going to solve questions related to each of the concept here. Right, so first I hope students have already joined the class. So let's just start our today's session with this concept of method of solving linear differential equation. So first, as I mentioned, we have to identify a typical linear equation format, that is a linear differential equation format. Right, so a differential equation is linear if the dependent variable y and its derivative appear only in the first degree. So here our dependent variable, so we'll be having 2 variables x and y, whereas y is a dependent variable and x is a independent variable. Right, so here in a linear differential equation, this dependent variable must be there and its derivative should appear only in the first degree, which means we should be having only dy by dx. So we cannot have our second degree, that is d square y by dx square. If it's that format, then we cannot identify or categorize that into our linear differential equation. Right. So the general form of a linear differential equation we can just identify here of the first order, which is given by dy by dx plus p is the constant, y is equal to q. So p and q here, right? So this is our general format. So there will be functions in terms of x variable. So this is our standard and general form of a linear differential equation. Dy by dx plus py is equal to q. So now the thing is how we are going to solve this. Right, so as I mentioned, where p and q are nothing but they can be either constant or there is a possibility of they can be functions of our independent variable x. Right, so there are two possibilities here we can have. So four possibilities we can say. So p can be constant, so this can be a function. So likewise we can have the permutation and combination here. So in general we can say the standard form here is dy by dx plus py is equal to q, where p, q are constant. So they can be constants or they can be functions in our independent variable x, that is functions of x. So there are two possibilities for this p and q. Right. So this is our linear differential equation. So now this type of differential equation, how we are going to solve this? So to solve any linear differential equation, we'll be required with the integrating factor. Right. So now in a linear differential equation, in order to solve that, we should be requiring a new term, that is a integrating factor. So now first thing here we have to find is an integrating factor, and after that we have to solve the linear differential equation here. So let's find the integrating factor here. So what is our standard linear equation that is given by here? Dy by dx plus p into y is equal to q, and the integrating factor is given by e power. So it is e power, so the integration will be in the power of e. So e power the p. So the p can be constant or it can be a function of x variable. So p integration of p dx. So this will be the integrating factor here. So once we could able to find the integrating factor, so the solution will be y into, so this y into integrating factor. So this will be our format of the required solution. So y into integrating factor is equal to integration of whatever the q value which we have here. So integration of q into the integrating factor, and after the integration we will be having the constant c. So this will be our required solution here. That means accordingly here y into what is the integrating factor? So e power integration of p dx is equal to the whole integration of q into here integration factor. So e power integration of p dx, and after the integration we will be having as usual the constant. So this will be the required solution of the linear differential equation. So here the only thing we will be required here is the integrating factor. So once we could separate the linear equation in this format, we could identify like this. Then we could easily find the integrating factor using the p, which is given by e power integration of p dx. So once we found out the integration factor, that is integrating factor, so this will be the required solution of the linear differential equation. So this is the methodology of solving any linear differential equation here. Right. So let's solve a question here. So if they have given a question which is not exactly in the format of linear, we could actually convert that into a linear differential equation format, and then we can simplify it as usual following the steps which we have discussed just now. So here you can identify a differential equation. So can you categorize this, whether it's a linear equation, differential equation or not? So the differential equation which we are given here is, so that let's write the standard form first. So dy by dx plus p into y is equal to q. So accordingly you can rearrange the differential equation which is given here. So let's rewrite as is the first one. So y log y dx by dy. So here it is dx by dy. So the terms can be rearranged. So no need to worry. If it is dx by dy, then what will be the terms? So dx by dy plus p into x is equal to q, where p and q are equations, functions in terms of in terms of y, or else some constants, right? So here plus x is equal to log y. So here I should be having a coefficient 1. So I am just dividing the entire term with y log y. So then it will be dx by dy plus x by y log y. And the other side it is 1 by y. Right. So now dx by, here dy, right? So dx by dy plus, so this entire term will become p. So now my differential equation has turned out to be dx by dy plus 1 by y log y into x is equal to 1 by y. So now you can identify from here what is p. So p is equal to 1 by y log y and q is equal to 1 by y. So now we can say p and q are nothing but functions in variable y. So that's what we should be having. So p and q can be constants, or else they can be functions in variable y. So now this will be our linear differential equation here after the rearrangement. So now as we have p and q, so the first thing here we have to do is finding the integrating factor. So can you guys quickly find the integrating factor here? So can you guys quickly find the integrating factor and let me know? Because here we have reduced that into linear differential equation format, and we have even find out the p and q values here, that is p and q functions here. So I'm just erasing this part, so you guys can find out the integrating factor and let me know. I'll just write down the equation here. Dx by dy plus 1 by y log y into x is equal to 1 by y. So this is our linear differential equation. So from here you can identify the p and q functions in variable y, and then you can find the integrating factor here. So what is integrating factor, guys? So integrating factor is equal to e power integration of p. So here in terms of dx, so it will be dy here, right? So e power integration, what is the p value? So p will be 1 by y log y dy. So we have to do the integration of this here. So e power 1 by y log y. So the integration of that power will be e power log of log y. Right. So e and log will get cancelled and we'll be remaining here with log y. So the integrating factor we end up having here is equal to log y. So now once we have the integrating factor here, so what is the format to get the required solution here? So y in general format it is y into, but here it is in terms of the reverse. So it will be x into the integrating factor is equal to integration of q into integrating factor plus the constant. So now as we have already found out the integrating factor, so let's substitute here and do the further integration and find the solution of this linear differential equation. Yes, Shivaranjani has already given the integrating factor log y. Okay, fine. So by this time you guys should be fast with this integrals and all, because we have done indefinite integrals, definite integrals, as well as area under curve, that is application part. So this entire thing are based on integrals only. So by this time you should be familiar and fast with this integration part of it. So this is our format for writing the solution of the linear differential equation, guys. So we have already found the integration factor. So let's just substitute that here. So x into log y here is equal to integration of what is cube? 1 by y, and integration factor log y dy here. Right, so just do the integration here. There is nothing to solve on the left hand side of the equation. So we have to further solve the right hand side here. I hope you guys can do this integration part. So here we are having log y as well as 1 by y. So here what we can do, we can take log y is equal to t. So differentiation of log y will be 1 by y dy, which is equal to dt here. So now let's just substitute the terms here. Okay, let's just erase this part. So far you guys have understood the solution, that is x log y is equal to integration of 1 by y log y dy. So now in order to do this integration part on the right hand side, I am going to take this log y is equal to t. So now the differentiation of log y will be 1 by y, as it's y it will be dy, and the other side dt. So now let's substitute the thing here. So in place of 1 by y and log y, 1 by y dy, we can substitute dt, and in place of log y we can substitute t. That means it is integration of t dt. So what is integration of t? T square by 2 plus constant c. So what we have assumed in place of t? So that is nothing but log y. So let's just replace it again, which will be turning out to be log y whole square by 2 plus constant c. So after this integration, the solution will be x log y is equal to log y whole square by 2 plus constant c. So this will be the solution here. So now we can, in order to eliminate one log y, we can divide the entire thing by log y. So then it will become x is equal to log y by 2 plus c by log y. So this will be the solution of this given linear differential equation here. Right guys, so I hope, okay, Shyam done, okay, good. So I hope most of you has already done. So this integration part is not that tricky, so you guys can do it. So as this is the first question, I just explained you the whole integration. So from the next, you can do it by yourself. I'll just give you the answer because we have already finished 3 chapters related to our integrals. So by this time, you should be familiar with this integration part and all. So next question, you can just take this as a homework. So it's for practice. You can take it as homework and work it on. So this is also related to the linear differential equation. So let's do one more question here. So you just, this is for practice. You can take it as homework, guys. So let's do the next one here. So the next question. So x plus 2y cube dx by dy is equal to y. So again, this is also in terms of dx by dy. So just give it a try. So first identify the equation and rewrite it in our general format and follow the steps required in order to find the solution here. So by this given equation, it is not exactly in our linear equation format, but we can rearrange that. So first we can just, here it's in terms of dx by dy. So it will be dx by dy plus p into x is equal to q. Whereas here p and q are either constants or functions in variable y. Functions in variable y. So have a look over the standard form of linear equation and try to rewrite our given linear equation here, linear differential equation. So if it is not possible to do in this format, you can rearrange dy by dx and then you can do it. So anyways, either it can be dx by dy or dy by dx, but it should be in terms of our linear format. So that's the whole idea here. So the only difference is if we are having dy by dx, so our p and q will be functions in terms of the variable x. Whereas if we are having dx by dy, then the p and q will be functions in variable y. So that's the only difference here. So let's see if anyone has already got it. Okay, Arun here, Tara here, okay. So I hope Sundays you guys are having exams. So I hope you guys are doing well. So if you have any doubts, if you want to repeat me any particular concept and anything related to that, you can please let me know so that I can plan it accordingly. Because we are actually finishing our syllabus, so differential equations, after that we'll be going to discuss linear programming. So that's a very small chapter, so by this month before itself we could actually finish the syllabus. So if you want me to do something related to like any doubts you're having any chapter in particular, you can please let me know so that I can plan accordingly. So here we are having dx by dy. So if I rewrite, so y by x plus 2y cube. As I'm having this in the denominator, I cannot separate it into two terms. So just rearrange it. So it will be dy by dx is equal to x plus 2y cube by y. So now I can separate this as x by y and 2y square. So let me erase this part. So if anyone has already, okay, let's just solve it. Okay, I hope there is a mistake here. So here it should be dy by dx only. Okay, it's just there is a mistake in the question, guys. So you can just rearrange things here. So x plus 2y cube into, here it will be dy by dx initially equal to y. So now I think you guys can solve it. So while rearranging it, we'll be having that issue. So let's just do it. So if initially, so just rearrange the term here, it will be dy by dx. So now it will be dy by dx equal to y by x plus 2y cube. So we cannot separate these into two terms because it's in the denominator. So let's just rearrange. So now it will be dx by dy is equal to x plus 2y cube by y. So now we can separate the right hand side term into two terms. So now here dx by dy is equal to x by y plus 2y square. So Arun, I hope now you can just have an idea because there is a small mistake in the question. I just changed it. So can you guys give it a try right now? So I'll anyway solve it, but you can just take 2 to 3 minutes and give it a try here. Okay, got it. Yeah, it's my mistake. So I just checked the question. So no issue. So now we have got the thing. So it will be dx by dy minus x by y is equal to 2y square. So this will be our standard linear equation format, guys. Right. So now it's a dx by dy and y terms in our functions p and q will be in terms of variable y. So now can you let me know the integrating factor here? Because once we get the integrating factor, we can find the required solution here. So quickly do it and let me know the integrating factor here. So quickly let me know the integrating factor, guys, here. So let's see if anyone has. Okay, Shivaranjani has already done it. Okay, fine. So can you let me know the solution, Shivaranjani? Or you can just give me the integrating factor also, no issues. Any of it will be fine. Okay, most of you has done it, Shivaranjani. So I'll just give you the final solution here. So integrating factor will be equal to 1 by y and the final solution will be x into 1 by y is equal to y square plus constant c. So this will be the final required solution here, right? So y square equal to x by y equal to y square, and this will be the integrating factor. You can just verify this, right? So let's move on to the next one, guys. So now, as I mentioned, we are going to discuss Bernoulli's equation. So this Bernoulli's equation is somewhat related to our linear also. So we are going to solve this by reducing into the linear form in order to find the solution of this Bernoulli's equation. Right. So first, let's just have an idea how a general standard form of Bernoulli's equation will be. Right. So a differential equation of the form dy by dx plus py is equal to q into y power n. So can you guys find any difference from which what we have seen the standard form of our linear differential equation as well as this Bernoulli's form of equation? The difference which we can identify here is y power n. Right. So if we could try to eliminate or divide this, we can get a linear form. Yes or no? So the standard Bernoulli's equation form we are having is dy by dx is plus p into y is equal to q into y power n. So this is the new term we are having from the linear form. Right. So again, where p and q will be either they will be constants or the functions of x. Right. So there is a possibility of here p and q can be functions of x and y in this Bernoulli's form of equation. Right. So now this Bernoulli's form of equation can be reduced into our linear form of differential equation. So if we could eliminate this y power n on the right hand side of the equation, then we can easily convert that into our linear form of equation in order to find the solution for it. Right. So how we can do that? By dividing by y power n by on the entire equation. Right. So this is the just standard form dy by dx plus p y equal to q y power n. So let's divide this by y power n. Then it will be 1 by y power n dy by dx plus p into y by y power n here and the other side q. That's it. Right. So this y power n can be written as y power minus n. So y power minus n dy by dx plus p into y power minus n plus 1 is equal to q. So this will be the next form after dividing the entire Bernoulli's equation, like and dividing entirely on both sides of the Bernoulli's equation by y power n. So this will be the result we will be getting. So now in this y power minus n plus 1, we can substitute v. That means in place of y power minus n plus 1, we are going to substitute v here. Right. So that it will be turning out the entire equation now going to be in terms of v. So we are just rewriting. So we are just recreating so that we can reduce the Bernoulli's form of equation into our linear. Okay, Shubharanjani has given the answer for the previous one. Okay, fine. So y power minus n. So we are going to substitute in that in place of v. So here it will be p into. So here in place of v, if we substitute, and that will be after differentiating. So dv by dx and all. So after differentiating here, so we will be dv by dx on the right hand side. So here it will be it will be 1 minus n y power minus n into dy by dx. So we are just differentiating this. Right. So now how we can substitute? So in place of dy by dx, in place of, so this is our reduced form, and in place of y power minus n plus 1 we have substituted v, and after differentiating we are getting this term. How we generally do substitution, right? And then we have to substitute the terms, like in place of dy by dx we have to substitute this dv by dx by 1 minus n y power minus n, and in place of v we have to substitute this y power minus n plus 1, and after doing all these substitutions we end up having the result to be dv by dx plus 1 minus n into p y is equal to 1 minus n into q. So now you can identify that it has been turned out into our linear form of differential equation. So there is nothing new here in this substitution. Whatever we will be doing in our general substitution so far we have done, that's the same thing here. So this will be the final term after reducing that into linear form of differential equation. So here we just have to keep it in mind, that is, to ensure that we have to convert into the linear form, we have to check the right hand side first. Because in right hand side we cannot have two variable functions. It should be one variable depending upon whether it's dy by dx or dx by dy. So that will be, from there we'll be getting our first step to start the conversion of the Bernoulli's equation to the linear differential equation, and from then after replacing that, it will, after dividing that, we'll be substituting v, and then after substitution you guys are familiar with how we'll be doing things from there, right? So let's just do one question related to this Bernoulli so that you guys can have an idea how will be the conversion and simplification further. So here comes the question, guys. So solve dy by dx is equal to xy plus x cube into y square. So can you guys quickly try and convert this Bernoulli's form of equation into linear and get the solution of this? This is not that much hard to solve it because you guys are doing the substitutions and all from very earlier. So there is nothing new here. So just we have to be keen. We have to be careful what will be the substitutions and all. That's it. So first thing, just rearrange the terms because sometimes what happens, by just rearranging itself, we could get. So I'm not asking you to find the entire thing. Just give me the integrating factor. That will be enough. So find the integrating factor here. So take your time, because by this time you should be solving this question by your own, because we are already done so many questions related to this integrations and all. There will be small concept that we have discussed just now. So just now we have even solved question related to our linear form of differential equation. So this is not that much difficult to solve it. So you guys can do it. And this is of course a JEE level question. So you have to be careful and try and solve it. So first just try to rearrange the terms and have a look what will be the result, and after that you can just solve it, like whether we can substitute something or what we can do. So Bernoulli's form will be dy by dx plus p into y equal to q into y power n. So by rearranging it, this given differential equation, we end up having it to be a Bernoulli's form of equation. So you can compare it here. So dy by dx plus p into y is equal to q into y power n. So the first step here will be divide by y power n. That means here divide the entire equation, both sides, by y square. So now it will become 1 by y square dy by dx minus x by y is equal to x cube. Right, so 1 by y square dy by dx minus x by y is equal to x cube. So now we have to substitute something. So whatever will be the y term, so that will be the substitution here. Right, so here whatever will be the p, that will be our substitution. So that means here minus 1 by y will be our substitution. So let's just be t. Yes or no? So minus 1 by y will be the substitution, because in the previous case it will be y power minus n plus 1 something plus of. So this turned out to be our substitution. So in the same place here we are having minus 1 by y. So that will be the substitution t here. Right, so you can take t, v, anything. It's up to you. So here the substitution will be minus 1 by y. So let's do the substitution and quickly find the first linear form of differential equation and then find the integrating factor for it. This will be our substitution. So let's just differentiate minus 1 by y. So this will be dt here. So minus 1 by y in the sense. So minus. So it will be plus 1. So you can do that and let me know the thing and substitute it. Finally, give me the integrating factor, guys. So it will be 1 by y square dy equal to dt. So let's just substitute that. We can say dy by dx or dt by dx. Anything will be the same thing. So in place of 1 by y square dy by dx here, we can take this dt by dx. Right, guys? And then minus 1 by it will be t here, x here, and the other side it will be x cube. So now this will be our linear form of equation in terms of t and x. So it will be dt by dx plus t into x is equal to x cube. So now what will be our integrating factor here? So it will be e power, right? So e power integration of p, right? So that will be x dx. So integration of x will be x square by 2. So which will be e power x square by 2. So this will be the integrating factor here. Right, so once we have the integrating factor, which is equal to e power x square by 2, we can write the solution. So solution will be here t into, so it will be t into e power x square by 2 integration factor is equal to q. So what is q here? X cube. So x cube, integration of x cube into e power x square by 2 dx. So this will be the solution. So you can further do the integration and get the answer. So if you guys could able to get the integrating factor itself, that means you are actually familiar with this conversion of Bernoulli's to linear, and then you can find the integrating factor. Right, so here the integrating factor will be e power x square by 2, because after the substitution of minus 1 by t equal to t, the linear equation we end up having is in terms of t and x variables, which is dt by dx plus tx equal to x cube. So from here our p will be x and q will be x cube. So the integration factor will be e power integration of x dx, that will be e power x by x square by 2. Right, so I hope you guys got an idea here. So let's move on to our next question. You can take this question also as homework. So for each and topic, I am just solving here one question, and I am giving you homework as a, like I am giving you one question for you guys to work it on as a homework for your practice. So let's move on to the next topic, that is exact differential equation. So this is a small topic. We'll just quickly go through this. So the differential equation m dx plus n dy is equal to 0. Right, where m and n are functions of x and y variables. So when we have any differential equation of format this, that means capital M dx plus capital N dy is equal to 0, where this m and n are not constants here. So these are functions of variables x and y. Then this typical differential equation of format m dx plus n dy is said to be an exact differential equation. And there is one more condition to satisfy, that is partial fraction, that is dm by dy is equal to dn by differentiation of with respect to x. That means partial differentiation of function m with respect to y should be equal to partial differentiation of function n with respect to x. So if this is equal, then the format of differential equation m dx plus n dy is equal to 0 is said to be an exact differential equation. So how we'll be solving this exact differential equation? So there are few steps we have to follow here in order to solve this exact differential equation. So let's just have a look over these steps or rules for solving the exact differential equation, which is of format capital M dx plus capital N dy is equal to 0. So the first step here is, first integrate the terms in m with respect to x, treating the y as a constant, which means if this is the function, we are going to differentiate this function with respect to our variable x, right? And considering this n, so if this is a function y, so we are going to consider this as a constant and going to differentiate that. Right, in the second step, the same thing, we are going to differentiate n with respect to y, that means dn by dy, while considering the x terms to be constant. Right, which means we are, in other words, we are doing here partial differentiation considering the other variable constant. Right, so after that, after these two steps, so this is here, we'll be having one equation. So here we'll be having one equation by differentiating, that is by integrating, So by integrating the terms of m with respect to x, treating y as constant, so equation 1, and here equation 2 will be other side, that means integrating y terms only by considering the other to be constant. So now we end up having here two equations. So now sum of these two above integrals that we have seen. That means here the first one is integration of m with respect to dx, and the second one is integration of yn with respect to dy. So after summing these two, they will be equal to some constant k. Right, if for example we doesn't have any n has no term which is of variable x, then we can directly have integration of m dx is equal to some constant, that is y. Because there is no y term here, so we can take the y term. So this is how we'll be solving the exact differential equations here. That means by taking one to be constant, one variable to be constant, and integrating with respect to the other variable, the same to the two steps, and finally summing up, and that will be the rules to follow here. So here we are having some exact differential equations which must be remembered. You can just have a look. You can say that these are some standard results here. So you can have a look over this and just remember this exact differentials here. So even for if you are having x dy minus y dx by x square, you can directly have it to be d of y by x dx plus dy divided by x plus y equal to. So likewise, you can just have a overall look over this exact differential equations. So from previous years papers, if you observe, there are I can say from recent papers there is no question from exact differentials, but it's good to learn, right? So that's why we are just learning. But mostly the questions will be from linear differential equation or homogeneous equations from this concept of differential equations. Right, so let's just solve one last question and then we can just wind up our session as well as our chapter of differential equations here. So here comes our equation. So we don't know what type of equation, what methodology we have to follow. So they just given an equation. You have to identify what is this type of equation and which methodology you have to obtain in order to solve and find the solution of this given differential equation. So yeah, so it's for your practice. So just give it a try, guys. So differential equation which is given here is x square dy plus y into x plus y dx equal to 0. So this is our differential equation which we have to find the solution. So here the methodology, what is this type of differentiation, nothing has mentioned here. That is, everything depends upon us. We have to identify it and we have to solve it. Okay, this one is easy. You can take it as homework. So let's do one question. Yeah, we can try and solve this question. So solve the this differential equation. So that's one you can just take it as homework. No issues. Give it a try by solving this, because this question is related to our today's concept only. So that's why I just want you to do this so that you can just have a base, or you can have a like idea of what we have done today. Here it will be dy, guys, dy by dx plus y is equal to cos x minus sin x. So it's exactly related to our today's concept only. So that's why I just changed the question to solve this. So you can just do it. So dy by dx plus y is equal to cos x minus sin x. So I hope you guys have already got an idea how to solve it. So quickly do it. So first let me know what type of equation is this. Which type of equation, you can just let me know. Yeah, Arun, I have just changed it. It's a mistake. It's a dy by dx. I just corrected it. You can just have a look. Come on, guys. It's easy. You can do it. So try to give it a shot by your own so that we can just have an idea. We can evaluate ourselves. So you guys can evaluate yourselves so that how much you just got it from our today's session. And if you have doubts, you can let me know. So if anyone got the integrating factor, because it's obvious that it's a linear equation, linear differential equation. So the differential equation which is given is dy by dx plus y is equal to cos x minus sin x, which is in our linear equation format, that is dy by dx plus p into y is equal to q. So what is the integrating factor, guys, here? Can anyone let me know the integrating factor quickly? Not yet. No one has given the integrating factor yet. Okay. So directly we can say that it's a linear form of differential equation, guys. So we have just discussed how to solve a linear form of differential equation. So first thing, we should find the integrating factor. So quickly find the integrating factor, guys, and let me know what it is. Okay, Sivaranjani has already given the integrating factor e power x, perfectly correct. So integrating factor is e power integration of p dx. So here what is p? Comparing our standard form. So p is a constant which is 1. That means e power integration of 1 dx, that is equal to e power x. So we got the integrating factor here. So once we got the integrating factor, what will be the required solution? So that is y into integrating factor, that is e power x, is equal to integration of q, that is cos x minus sin x, into the integration factor here. So you can do the further integration. So I am not going to solve it because we are already familiar of doing this. So I'll just give you the final solution here. So your final solution will be equal to y equal to cos x plus c e power minus x. So you can have a look. So just give it a try, this integration, and you can let me know, because here we have to apply our method of integration by parts and all. So I hope you guys are, we are already familiar with this integration by parts and all. So you guys can solve it, this further question, right, further solution. So that's all for today. So with this, we finished our chapter of differential equations. So we are almost done with our syllabus. So there is one chapter that we have to cover, that is linear programming. So that we are going to start in our next session. So we are almost end of our syllabus. So if you have any doubts, or if you want any particular concept that you want to learn, like you have doubts and all, you can let me know so that I can plan accordingly. So if you want a lot of questions for some typical particular topic, so that also you can let me know so that I can plan accordingly. So from our next session. So yeah, that's all for today. So we have finished our chapter of differential equations, and in our next chapter we are going to start our next chapter, that is linear programming. So that's all for today, guys. So thank you. So we'll just meet in our next session. Thank you, guys.